Okay, guys, we will start now. I am hoping that you can see my screen. Is my screen visible?
Yes, sir.
Okay, we will start. Welcome everyone. This is a problem solving session for analog electronic circuits course, and I hope that all of you have gone through problem the first week's lectures. And so before I begin the problems that I have got for this session, will anyone wants to does anyone wants to just a minute. I think everyone is there. Okay, so I am audible, right?
Yes, sir.
Yeah. So before we start the problems that I have got, does anyone has any doubt from session the first week's lecture? Have you guys got a chance to go through the go through the assignment and course content of the first? I hope everyone has gone through the first week lecture. Am I right in assuming this?
Yes, sir.
Okay, so no issues in first week lectures, I imagine.
Yes, sir. Sir, when we are while we are considering the small signal analysis, after derivation or derivative, we came to conclusion that a derivative is much less than equal to one. Then only we consider it as a small signal analysis. Now,
Correct.
so if in the case if it is not much less than equal to one, if it is slightly less than means not much more less than equal to one, if it is less than equal to one, in that case how should we deal with it, sir?
While designing the circuits, so mostly the circuits are non-linear in nature. All the active circuits mostly are non-linear in nature, and I think you guys know. Can any one of you answer that why circuits are generally non-linear in nature? Like
Because of
why?
the power amplification, we need if we don't have any non-linearity, we cannot get a power amplification. We need a certain weak non-linearity to get a power amplification.
Correct. So you need certain non-linearity to get power amplification. So, like, how do you design? Just a minute. So, how do you design? How do you design any kind of circuit? Are there more people who are willing to join? Just a minute. Let me. Okay, how do we design circuits? Is there is a spec called total harmonic distortion or non-linearity. Okay, so for example, you let's say there is an amplifier that has got a curve of V out is equal to F times Vn, and for example, let's say like at some point for biasing it through, and let's say this particular function is a nonlinear function. Now what we have is like the gain. Let's say what we will have is dvo by dvn is equal to some derivatives of f dash times vn, correct? Now let's say you work out the math and see that you want, let's say, a gain of 100 out of this. So you try to get the gain. And if your signal, like the incoming signal, that is V naught, is not a small signal, that means to say that f dash times V in times dV in is not much less than 1, then what will happen is there's will be some amount of non-linearity that due to this function will start creeping in. So what will happen is, let's say when you are doing actual when you are doing incremental analysis, then your output dvo will be, I mean vo plus dvo will be equal to some f v in naught of, this is the point where you bias your device, plus f dash times v in times dv in. Now, if let's say this quantity starts becoming larger, then this approximation will fail, and then you will have to rely on the original equation, that is f naught is equal to f times v in. Okay. So in that case, what will happen is, let's say you gave a sine wave at the input. Now, when the sine wave's amplitude is too large, it will pass through a nonlinear function, and you will get harmonics of the sine wave. So what will happen is, if your small signal approximation is not being met, then at the output you will have distortion in terms of total harmonic distortion. For example, this like at input, when you give a tone of f naught, so this is time domain, this is frequency domain. If in the input you give a tone of f naught, if it was a linear system, what you will get at the output? Can anyone tell? Hello.
Yes, sir.
Yeah, if it is a linear system, completely linear system, if you give a tone at the input with a frequency f naught, then
Hmm.
what can you expect at the output?
Sir, mean we can expect 2 times of f naught, sir.
Yeah, I mean with gain, no, not two times of f naught. So first of all, like, will there, if this is a completely linear system and a time invariant system, will there be any frequency at the output other than f naught?
No, no, not because of
Uh,
it is a linear system.
it is a linear system, hence there won't be anything like at the output apart from f naught. In f naught there will be some phase shift and some amplitude gain. Okay. Now let's say it was a non-linear system. Let's say it was non-linear, like it has some v in square plus v in cube, something like this. So in that case, what will happen is, instead of f naught, you will get some f naught with some gain. Let's say there is a gain of a. Apart from that, you will get certain other frequency components at 2 f naught, 3 f naught, and so on. Due to which, what will happen is, you will say that your system now has distortion. So how you will measure the distortion is, like the strength of the fundamental tone divided by the strength of the all the harmonics that are present in the system. This you will coin as a term known as total harmonic distortion. So like the way to analyze or way to characterize a nonlinear system is, you one way of doing this. Actually, like there are multiple ways, and like complete detail of it you can learn in advanced classes. But like one way of analyzing non characterizing a nonlinear system is by looking at its total harmonic distortion, that given that you give a input tone of f naught, what is the ratio of the harmonics that you get at the output. So and that happens when your input your small signal model gets when your small signal model is not good enough, and you have to you instead of the linear equation, this linear equation, you have to rely on the actual non-linear equation that that particular device had. Does this answers your question?
Yes, sir. Means in the class, sir give example with the help of diode, no, sir.
Okay.
There with while derivating at the end he will come to a conclusion if the derivative is much less than or equal to this thing. then only it is incremental. I mean, we can consider if it doesn't follow these condition, means that intermodulation will be going to occur in even diodes also.
Correct. Like intermodulation or second order distortion, any sort of distortion will occur in like whatever nonlinear system that you have.
Means in diodes how it will occur, sir? Means previously you explained with the MOSFET, no? If it is a diode, how it will impact?
So, for example, you can see it this way. I will just put one thing: non-linearity in a diode. Okay. So, what is the transfer function? What is the function that relates diodes current and voltage? Can some anyone of you tell?
I equal to is exponential of VB by eta VT minus 1.
V by eta Vt minus 1. Okay.
Yes, yes,
So, what happens is, any function, that you are familiar with the concept that any function can be written in the form of its Taylor series approximation. This thing,
yes, sir. Yes, yes.
Yeah.
Uh,
So, what we will do is we will try to. So, what is the formula for Taylor series? Let's say we have a function of fv. Uh, fv, and we want to find its Taylor series approximation for an input centered across v naught. So what we will get is fv naught plus some
First derivative.
delta v times f dash of v naught plus delta v square by 2 factorial times f double dash of v naught, and so on. Correct? Is
Yeah.
this clear?
Yes, sir.
Yeah. So now, we have f of v is equal to e to the power v times v by eta vt. Okay. So what will be its Taylor series? Its Taylor series will be, let's say, there is some biasing voltage called v equal to vd. Okay. At that biasing voltage, your Taylor series will be e to the power vd by eta vt plus, what is the derivative of this?
1 by eta VT, sir.
1 by eta Vt times e to the power Vd by eta Vt. And here we have some delta dVd. Okay. Plus the second derivative will be dVd square divided by eta Vt whole square times 2 into e to the power Vd by eta Vt. Okay. And so on. Then there will be a cube term, then there will be a power 4 term. These things will keep on happening. So what will happen is, if this dvd becomes sufficiently large, for example, now let's say if dvd is sufficiently small, then what you can do is, if dvd is small, much less than, so if this particular quantity, this complete quantity is much less than 1. Okay. So what will happen is its square will be even lesser than 1. Correct?
Exactly, exactly, sir.
Yeah. Its cube will be even much more lesser than 1. Then in that case, you can neglect these quantities. However, if it is not the case, these quantities are not significantly less than 1, or as a matter of fact greater than 1. In that case, what will happen is, all these terms will come into play. Now, let's say if your Vd was a sinusoidal signal of sine omega naught t, in this case, what will happen is, the sine omega naught t, the dvd square will result in sine square omega naught t, and sine square omega naught t has a frequency component of 2 omega naught. The dvd cube term will have a frequency component of 3 omega naught. So if you apply a voltage across a diode, as for example, there is a fixed voltage of Vd plus some signal of dVd, and it's a sine wave. If the sine wave, the amplitude of the sine wave is large enough that this dvd by like eta vt is not much less than 1, then what will happen is, like you in the current you will have the omega naught term, the omega naught tone plus even like further tones or at 2 omega naught, 3 omega naught, 4 omega naught, and so on. And the strength of these tones will depend on how like small or large your dvd is. Okay, now let's so generally when you design systems, it's not that like it's not a black and white thing, like your system is linear or your system is not linear. It doesn't work like that. It's always a gray area, that your the system will always be non-linear, because these terms won't go to zero. They will go to a very negligible value, but they won't go to zero. So in those cases, what you do is like some system level engineer will come and tell you that, okay, I need like this system should have your total harmonic distortion greater than this amount, and accordingly you will decide what maximum dvd you can give to this diode, so that your total harmonic distortion does not exceeds that particular amount. And if it does not exceeds that particular amount, then you will say that your system is linear enough for you, as far as your application is concerned.
Clear, sir.
Okay. Any other doubts with as far as first week lectures are concerned? Okay, if there is no other doubt, we will go through some questions that I have prepared for the first, based on the first week's course material. So let's start with this question. Just a minute. So this question is basically takes into account a voltage regulator made as so the problem statement I will read out loud. The voltage regulator takes an input of an input takes takes as an input a high voltage input that can vary widely, and generates an output voltage that remains constant irrespective of the input voltage or the load that the load current that is drawn. So, and in this figure, this is a voltage regulator. So how does it behaves as a this is a crude voltage regulator, there are some like series of three op amps that are connected in forward bias fashion. Can anyone tell why these op amps I'm saying is forward bias, looking at this diagram? Anyone?
Sir, based on input impedance, sir.
No, not on input impedance. See, based on the input voltage varies from 6 to 12 volts, and the output will also
Yes,
be a
sir, I
positive
get the
value.
point.
Yeah, correct. Output will be a positive value, so you can assume that these op amps will be in forward bias condition for the reliable region of operation. And it's mentioned, okay, here that 6 volt to 12 volt your input can vary, and these three diodes are identical. The load Talpa, can you mute yourself while you are not speaking? There is a little bit of disturbance. Yeah, thank you. The load is represented by a resistor of a value RL that can be that can vary from anywhere from 5 kilo ohms to infinity, and it's mentioned, one of the points for this diode has been mentioned, that when RL is equal to 10 kilo ohms and Vin is 9 volts, then the output voltage comes out to be 2 volts. Okay. So what is asked is determine the saturation current of diodes. So can anyone tell me, can anyone give any idea like how to attack this problem? So, okay, let's go step by step. We know that these three diodes are equal. And let's say there is some output voltage. If all these three volt diodes are identical, and the total voltage across this series combination of three diode is V naught, then can anyone tell what will be the voltage across one particular diode?
V naught by 3, sir.
Correct. So, if you know that one particular diode will hold V naught by 3, and what will the current? The current will be same in the three all the three diodes, because these are connected in series. Correct?
Yes, sir.
Yeah. If the current, so what is the current through the diode? Let's say the current through the diode, this complete branch is ID, the diode branch. So what will be the equation with which this ID current will be governed?
Is
Is
exponential of
exponential of
V naught
V naught.
by eta Vt.
Eta, in this case, since no eta is mentioned, so you can assume eta to be equal to 1. So V naught by Vt, and like we know that this is a pretty large voltage. So what is the value of Vt?
26 millivolts, sir.
26 or 25 millivolts. Let's say 25 millivolts. Okay. So it's a pretty large. So the output voltage of 2 volts, V out, let's say, so it will be 3 times. Your voltage will be V naught by 3 times Vt, and your output voltage is around 2 volts. So V naught by 3 will be around some
0.66.
point 0.66 volts. And you can imagine that 25 millivolts, like 0.66 volts divided by 25 millivolts, will make this exponential so large that the minus one term that you have, you can ignore this minus one term. Okay. So your equation becomes ID is equal to Is of e to the power V naught by 3 Vt. This is it. Okay. Now can based on the this expression that is written over here, that when RL is equal to 10 kilo ohms and Vin is 9 volts, what will be the output voltage is 2 volts. So depending on this information, what information can you what all information can you plug in to this equation? So you need to find the saturation current of the diodes. Correct? So, and this condition, all these conditions are given to you. So what do you think, from these conditions, what all things can you infer and plug it into this equation to get your saturation current?
Sir, we need to plug in the ID value, a V out value, to plug
Correct.
in the IS value.
To find the IS value. Now, what is the V out value?
V out is a point not 666.
No, no, that is V out by 3.
Oh, sorry. Yeah.
That is V out by 3. V out is 2 volts. Okay. So now we have, okay, now we have ID is equal to IS times 2 by 0.075. Okay. Do you understand how I get 0.075? It's basically 3 VT, 3 times 25 millivolts.
Yes, sir.
Yeah. Now, like, how will you find ID?
Sir, we can find it by using nodal analysis, sir. V in minus V out. With this equation, we can find out
Okay, so what is the value of V in that is mentioned for this particular case?
9 volts.
9 volts, correct?
Mm.
9 volts. What is the series resistance? The series resistance is of
1 kilo ohm.
1 kilo ohm. 1 kilo ohms. Then we have this diode combination that is going to draw some current of ID that we need to find. And what is the voltage at this node that is given?
2 volts.
2 volts. And what is the load resistance? 10 kilo ohms, correct?
Mm. Yes.
So, what will be the value of ID? Please, anyone quickly calculate and tell it to me. Yeah, the session is being recorded, but like if you are there in the session, please try to attend it live so that it can be interactive. You can ask your doubts. You can try to solve the questions on the fly, because I will try to make this session interactive so that you can benefit from the problem solving. You can acquire the problem solving skills. So it will be better if you go through this session. Okay, so like quickly, can anyone tell me what will be the value of ID in this condition?
Sir, ID would be 7 milliamperes, sir.
Sorry,
7 milliamperes.
let's try to see if it is correct. So, what will be this current?
Okay, okay. Yeah. Yeah, that is
What will be,
7 milliamperes. Correct.
this is 7 milliampere, right? So,
Yes,
9
yes.
volt minus 2 volt, like 7 volt divided by 1 kilo ohm resistance, you have 7 milliampere. What will be the current that will be drawn from the load resistor?
Sir, 2 by 10.
Yeah, 2 by 10. What is that?
Yeah, 0.2 milliamperes.
No, 0. Yeah, correct. 0.2 milliamps. So what is the value of ID? It's equal to 6.8 milliamps.
Yes, sir.
Okay. So now you know your ID is 6.8 milliamps, and IS, then you have e to the power 2 by 0.075. Okay, so from here, value of the saturation current, can anyone tell what will be the saturation current that you will be getting? Can anyone quickly calculate this particular value?
Sir, 3.812.
Yeah, it is how much?
3.812 into 10 power 11.
Divided by 1 second. Correct. 3.812 into 10 to the power 11. Correct.
Yes, sir.
So now what will be the value of the saturation current that you will be getting?
17 picoamperes.
70, so 6.8 divided by 3.812, that comes to correct. So it will be 1.78 into 10 to the power minus 14 amperes. And if you take, so it won't be picoamperes, it will be 17 femtoamperes. It will be 17.8 into 10 to the power minus 15, correct? And
Yes, sir.
10 to the
Yes.
power minus 15 is femto. So the value of saturation current comes out to be 17 femtoampere. Is this clear to everyone?
Yes, sir.
So saturation current we have found out. Now let's move to the another question. Determine minimum and maximum values of output and values that the output can ever take for the given ranges of V in and RL. So I will redraw the circuit over here so that we need not to go back time and again. So your V in can vary from 6 to 12 volts. Your RS is given out to be 1 kilo ohms. Then you have this voltage regulator, and then you have an RL that can vary from 5 kilo ohms to all the way up to infinity. Okay, so you need to tell what will be the maximum and minimum value of output voltage that can come given the ranges of input voltages, and the output resistances RL. Okay. So, can anyone tell me what will be the scenario for the output voltage to be maximum?
Open circuit, sir. If it is open circuit, output voltage should be maximum, sir.
Open circuit as in what will be the value of RL?
It should be infinity.
Okay. So, for a condition of VO max, my circuit, what will be the input voltage?
Yeah, 12 volts, sir.
12 volts. So, 12 volts, you have then 1 kilo ohm of resistance. Then you have V naught, and over here this diode combination, and the output voltage is open circuit. Okay. So now see, the one way to solve this is to actually go and solve the nonlinear equation that you have, basically ID is equal to Is times e to the power V naught by 3 Vt, and compare it with the value of 1 kilo ohm of resistance. Okay, but that will be a very cumbersome way to solve this problem. So what we will assume is, like we will try to incorporate the things that we learned in our class of small signal analysis. Okay, so what we will assume is, uh, this particular circuit, when it had 9 volts of current, and 1 kilo ohm of this particular resistance, and okay, from there, never mind. So here what we saw was that when an ID of 6.8 milliamp is flowing through this diode, the the total series combination of diode is producing a voltage of 2 volts. Okay, so with this information in mind, what we can do is we can try to find, like incrementally, this particular element will behave as a linear resistor. Let's assume that the input voltage is 9 volts. When the input voltage is 9 volt, we'll calculate what will be the incremental resistance of this particular diode circuit. And on top of that, when there is a plus 3 volt deviation from the input voltage, that is from 9 volt to 2 volt it goes, or there is a minus 3 volt deviation of the input voltage, that is it goes from 9 volt to 6 volts, then we can find out what will be the change in the output voltage based on whatever incremental resistance we have. Then our circuit will become linear. What we will do is now we will try to find out the incremental resistance of this series combination of diodes. So what we will have is we have this equation that ID is equal to the ID, that is the current flowing through this series combination, is equal to Is times e to the power V naught by 3 Vt. So, to find the incremental resistance, what is incremental resistance? Can anyone tell?
So means if it is approximation, sir. Means first derivative of
Change
it
in
will be
voltage
much less.
divided by, correct, a change in voltage divided by change in current.
Yes, sir. Exactly.
Okay, that is dV naught divided by dId. So, can you find dV naught divided by dId from this equation? Let's
Yes,
try
sir.
to derivate it. So, it comes out to be dId divided by dV naught is equal to Is into e to the power V naught by 3 Vt divided by
3 VT.
dVt. Okay. Now, your what you want is if you reciprocate it, then you get dV naught by dId, that is equal to R incremental of this complete series combination, that is equal to 3 Vt divided by I naught times e to the power V naught by 3 Vt. Correct?
Yes, sir.
Okay. Now, what is the value of sorry, this is Is. What is this particular value?
ID, sir.
ID. And what is the value of ID?
ID
For V
11.
naught of 2 volts, for V naught, the output voltage is 2 volts, right? So for V naught of 2 volt, what is the value of ID?
9, sir. 9.
6.8 milliamps. We calculated that, right?
Yes, sir. Yes, sir. Correct.
Yeah. So what we have over here is 3 Vt divided by 6.8 milliamps is going to be our incremental resistance. Now, plugging in value of Vt as 25 millivolts, can you guys quickly tell me what is the output resistance that you are going to get?
Sir, 11 ohms, sir.
11 ohms. Okay.
Means that milliamperes and that millivolts will be get cancelled.
Yeah. So you will have basically 75 divided by 6.8, and that comes out to be roughly not 11 ohms, 11.02. Okay. Thank you, Sinduri. So 11.02 ohms you get as your this thing, your incremental resistance. Now it will be much easier to find what will be your minimum and maximum values. Okay. So what you can do is you can replace this particular diode connection with 11 ohms of 11.02 ohms of this thing. Now what will happen is what is the incremental change in the so now we will forget about what the actual biasing point of the circuit was. The actual biasing point of the circuit was 9 volt at the input, and for that case you know that this is behaving as an 11 ohm resistor, correct? Now what will since we are trying to find out V out max, and we say that V out max will be when your input voltage is maximum. So what will be the incremental voltage that will be applied at the input?
2, 3 volts, sir.
3 volts, correct? 3 volts. So what will be V out? 11 divided the simple voltage divider, into 3 volts. Is it clear?
32.64 millivolts, sir.
Okay, 32.64 millivolts. Okay. So when your value of value of input voltage is incrementally increasing from 9 volt to 12 volt, the incremental change in the V out that you observe is of 32.64 millivolts. Now this 32.64 millivolt is residing over what particular voltage that you had initially? So it's residing over 2 volts, correct? Remember, initially the condition was given was that initial, if the voltage is 9 volt, output resistance is of 10 kilo ohms. So at that time, your voltage was 2 volts. Based on that information, we found out the incremental linear model of this diode device, and on that we performed incremental analysis by applying an incremental voltage of 3 volts, and we found out that the incremental increase in the voltage, output voltage is of 32.64 millivolts. So this particular voltage will be riding over the original biasing point, that is of 2 volts, initial 2 volts. Okay. Okay. So your V out max will be equal to 2 plus 0.032 sorry 0.032. So your maximum output voltage will go to 2.032 volts. Okay. Is this clear?
Yes, sir.
Okay, now let's see what minimum value of this voltage can go to. For minimum value, what is the input voltage that needs to be provided?
-3 volts.
Minus 3 volts or 6 like incrementally minus 3 volts, correct? This won't change. This is 1 kilo ohm, and this is 11 ohms of resistance. What is the load resistance that needs to be there for the voltage to be minimum?
Sir, it should be low resistance, sir.
Low resistance, and the lowest
5 kilo ohm.
resistance that was given was 5
5
kilo
kilo
ohms.
ohms.
Okay, 5 kilo ohms. So, can anyone quickly tell what will, if like dV in is minus 3 volts, so what will be dV out? What will be the parallel combination of these two guys?
Sir, 11 ohms approximately.
Approximately 11 ohms. So yeah, if you take it approximately as 11 ohms, then your dV out will be just the negative value of whatever you got over here. So your VO min will roughly be equal to 2 minus 0.032 volts, and what this comes out to be?
1.968.
1.968 volts. So you have got the range of minimum and maximum voltage that you are ever going to achieve from this circuit. Okay. Now we move to the third part, that is line regulation of regulator, which is the ratio of the line regulation is also defined. It is the ratio of the change in the output voltage when V in varies from 6 volt to 12 volts, and the nominal output voltage with respect to the nominal output voltage, that is when V in is 9 volts. Okay. So load resistance is given as 10 kilo ohms, and V in when 9 volt, when you have V in of 9 volt, you know the output voltage is of 2 volts. So in this case, what you need to find actually is that your input is varying from the V in naught, that is of 9 volt, plus minus 3 volts, that is from 6 volt to 12 volt. Your series resistance of 1 kilo ohm is here, and then you have this incremental resistance of 11.02 ohms, and your output load resistance stays same of 10 kilo ohms. Okay, so you need to like when it is 9 volt, you know the output is equal to the output is equal to 2 volts. Okay, when it is plus 3 volt, that is it goes to 12 volts. We saw that like you calculate what is so plus 3 volt, you need to calculate what is the what is roughly the incremental output voltage. When it is minus 3 volt, you need to calculate what is roughly the incremental output voltage. You need to subtract that, and that will be divided by the nominal output voltage, that is of 2 volts. This will give you line regulation. Similarly, for load regulation, you will keep V in as constant and vary this output resistance from 5 kilo ohms to all the way up to infinity, and see what is the change in the output voltage. So, like that will give you the load regulation. Now, can anyone tell which will be a higher quantity, line regulation or load regulation? That means, uh, does the voltage varying from 6 volt to 12 volt cause more impact on the output voltage, or the load resistance varying from like 5 kilo ohms to infinity cause more impact on the output voltage? Which of these two phenomena causes more impact on the output voltage? Can anyone guess?
Sir, could you repeat again,
The
sir?
voltage.
Yeah. So my question was that does voltage variation cause more impact on the output voltage, or the load variation cause the more impact on the output voltage? Raj
The
Aryan
voltage
told,
variation.
yeah, voltage. Can you explain why?
Because sir, the incremental resistance of the diode is 11.02, which is equal to the load, which is nearly equal to the increment in load resistance. So
Correct. So you mean to say that when the parallel combination of a kilo ohm resistor is taken with an 11 ohm resistor, the change in the overall output resistance will be much smaller. Correct?
yes, sir. Yes, sir.
Yeah. So that's why, but in that case, even in that case, your change in input voltage varies from all the way to minus 3 volt to plus 3 volt. So in that case, like if let's say if your input voltage is held constant at 9 volts, your output resistance will be roughly 11.02 ohm, no matter whatever this load variation is happening. Okay, because 5 kilo ohms is also like 5 kilo ohms in parallel to 11.02 ohms is also roughly 11.02 ohms, and infinity parallel to 11.02 ohms is definitely 11.02 ohms. So your since nothing is changing in your circuit, your load regulation will be much smaller. But your line regulation, when there is a variation in the input voltage, then that particular thing will directly come at the output with some attenuation factor, of course, but there is a significant change in the overall circuit. So in that case, your line regulation will be a much severe impact, will have much severe impact on the output voltage. And does everyone understands this?
Yes, sir.
Okay. So we are done with this question. Now I hope that this gives you appreciation for why incremental analysis is important. So if let's say you were not finding the actual like incremental circuit of the diode connected the diode combination and was trying to actually find it using the transcendental equations that you get, so that will involve something like x is equal to some function some something something into e to the power x by 3 v naught, something like this. Now this kind of equation, whatever you do, you cannot solve it by hand. You will either have to use some numerical expression or you will have to take help of MATLAB to solve this. But if you assume that the variation is x, variation in x is small enough, that is variation in input voltage is small enough, and make the incremental take the incremental resistance over here, in that case you can come to the answers quickly. Now but you should always keep in mind that you make sure that your incremental analysis is working fine. And how will you do that? How did we come to this 11.02 ohm like as a like model for the complete diode picture? What we had was id is equal to is into e to the power v naught by 3 vt. And if we take the Taylor series of this equation, what we will get is is times e to the power v naught by 3 vt plus is by 3 vt into e to the power v naught by 3 vt times some dv naught square, that is the output sorry dv naught, plus is upon 3 vt whole square into 2 into e to the power v naught by 3 vt times dv naught square. So what you can do is, let's say if you neglect the second order term, if you have neglected the second order term, then you will eventually arrive at the incremental resistance that you had, and then you will have to solve a linear equation in order to find the voltage changes. Let's say you are not confident enough that your second order the first order approximation is good enough. What you can do is you can also include the second order term. So now you have a quadratic relation between id and the output voltage v naught. You try to recalculate the dv naught that you want, and just check that how much variation that you have seen in the dv naught when you neglect the second order term, and dv naught when you include the second order term. If you find out that this variation is not large enough, then you know that okay, incremental analysis is going to work. Is it clear?
Yes, sir.
Okay. So I hope this gives you some motivation to why incremental analysis is necessary. Now we will move to other question. Now before I move to other question, you guys have started. So you guys have been introduced with MOSFET characteristics, right?
Yes, sir.
Yeah. So can we quickly revise what is the okay MOSFET characteristics? So can we quickly revise what were the characteristics that we have seen? So for let's say for an NMOS first. So what all parameters are given for an NMOS? Let's say it's a 3-terminal NMOS. Let's not go to a 4-terminal device. Let's say it's a 3-terminal NMOS and your source and body terminal are shorted to each other. Okay. So in this case, what are the three regions of operation?
The triode region and saturation region.
triode region,
Cutoff
saturation,
region.
and cutoff
and
region.
cutoff region. Yes, sir.
What is the condition for triode region?
Sir, when VGS is
It should
greater
be
than VT and VDS is greater than VGS minus VT.
VGS is greater than VT and
VT and VDS is greater than VGS
VDS
minus
should
VT.
be less than or equal to
less
VGS
than,
minus
less than. Yeah, correct. Less than
Less
is
than, less than
equal to VGS minus VT. Okay.
VT.
So yeah, this is the this and what is the current equation in this particular region?
Sir, half um,
I
mu
is
naught C1
come again.
half. Sir,
ID should be
half
mu and W by L, VGS minus
yeah,
VT times
Mu and
VDS minus VDS square.
mu and Cox. Okay.
yeah. Yes, sir.
Mu
Mu
and
and
Cox
L,
W by L into VGS
VGS
minus VT
Minus VT, VDS
times
minus
whole square. VDS
times
square,
VDS minus
VDS square by 2.
VDS square
minus
by 2.
VDS square.
half
VDS,
VDS square.
yeah, correct. So this is the equation for triode, and what is the equation for what is the condition for saturation first?
Sir, VGS is greater than VT.
VGS should be greater than
VGS
VG.
should be greater than VT, and
VDS is greater than VDS minus VT. VGS minus VT.
VDS is greater than VGS
VGS
minus
minus VT.
VT. What is the current equation now?
Sir, half mu
ID
n
should be
C of
UX
Mu
by
and
2
C by 2. Yeah, half I have done. Half I have written.
times
W by L
VGS whole square.
W by L
times
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 VGS
VGS minus VT to the
VT.
whole square.
Okay, to verify these two equations, what you can do is just a minute. How will you verify that this equation and this equation is correct?
VGS should be greater than VT.
No, that is correct. But what you can do is at boundary condition, let's say VDS is just equal to VGS minus VT is the boundary condition. You guys agree?
Yes, sir.
That will be a boundary condition between triode and saturation. In that case, plug in the value of so VGS is equal to VDS is equal to VGS minus VT. Okay, this is the boundary condition. If you try to find out the current from the triode, what do you get? I is equal to mu n Cox W by L times VGS
VGS minus VT
whole square, because VDS is also equal to VGS minus VT
Yes,
minus VGS minus VT whole square by 2,
by 2
and that comes out to be half
half mu n
mu n
C of
Cox
W by L
W by L times
VGS minus VT
VGS minus VT whole square.
VT whole square.
This is the same equation as the saturation current. Okay,
Yes, sir.
that means that mind it, in nature no curve that you see is is a discontinuous curve. You always find continuous curves. So it basically does something like this. And for cutoff, it's obviously VGS is what is the condition for on VGS?
VGS is
Less than VT.
Less than VT, and the current is
0.
0. So the current will start from here. Let's say this is some VGS. The current will start from here, and after some time it will saturate. And if you see that at the saturation point, this is VDS, sorry, and this is I out. At the saturation point and the triode point, whether you calculate the current's value from saturation equation or the triode equation, you have to get the same value. Is this clear?
Yes, sir.
Yeah. Other thing is, now these equations you should keep in mind because these are fundamental equations. That is correct. But while solving the questions, you need to be quick. So for that, what you can remember is, let's say this is the source terminal, this is the drain terminal, and this is the gate terminal. So for saturation, the condition that you had was that VDS should be greater than or equal to
VGS minus VT.
VGS minus VT. Now, if you see, it's VD minus VS should be greater than equal to VG minus VS minus
VS
VT.
minus VT.
You can get rid of these VS terms.
Yes.
Okay. So VD must be greater than VG minus VT.
VG minus VT.
So, for quick back of the hand calculations to for the transistor to be in saturation, let's assume that it's in. Let's assume that the cutoff limit is met. That you just check, and if the cutoff limit is met for the transistors, like limit the boundary condition for triode and saturation, your like you must remember this statement, your drain voltage can go at least can go 1 vt down below your gate voltage, so that your device remains in saturation. If your drain voltage goes more than 1 vt below your gate voltage, your device goes
Yeah,
into
so right.
Okay. So in this thing, you will get you don't need to actually calculate the VGS, VDS, and then compare the equation. You just quickly just remember this thing. Your gate voltage can be like your drain voltage can go 1 VT below your gate voltage. Conversely, your gate voltage can go 1 VT higher than your drain voltage. Is are these two statements clear?
Yes.
Yeah, so I'll write it over here. Assuming device is on, that means VGS is greater than VT. If this condition you know that is true, in that case, VD can go 1 VT below the VG for device to be in saturation. Conversely, VG can go 1 VT above the VD for device to be in saturation. You understand this? You should keep this in mind for quick back of the hand calculations. Okay. Now this was the story of your NMOS. Okay. Now for PMOS, you know VT is a negative quantity. Let's draw a PMOS over here. This is no. What is this node?
Source.
Source, correct. What this is gate and this is drain. Okay. So VT is a negative quantity, and the VS now VGS is a negative quantity, VDS is a negative quantity. Source will always be a higher voltage. Okay. So like instead of remembering two different equations, what you can just do is in the NMOS equations only, you basically replace VT of PMOS by the modulus of VT, and instead of VGS, you write VSG, and instead of VDS, you write VSD, and you guys are covered. Okay. So now for triode, VSD must be, VSD is less than or equal to VSG minus of modulus of VT. Is this clear?
Yes,
What
sir.
is VSD? VSD is this voltage. This, if it is less than VSG, that is Vs minus Vg minus modulus of Vt, then you are in triode, and the current equation comes out to be mu p Cox W by L times VSD minus VSG minus modulus of Vt times VSD minus VSD square by 2. Okay. And again, the saturation, VSD is greater than or equal to VSG minus modulus of Vt. Okay. So your current becomes mu p Cox W by L, half of this, times VSG minus modulus of Vt whole squared, and your cutoff VSG must be VSG is less than modulus of Vt, and your I is equal to 0. Okay. Nothing you have to do. All you have to do is remember the NMOS equation, and whenever you encounter PMOS, replace VDS by VSD, VGS by VSG, and Vt by modulus of Vt in the NMOS equation that you remembered, and you will get the equations for PMOS. Is this clear?
Yes, sir.
Okay. So now you need not to remember, okay, here it has to be plus or minus, or sometimes it becomes confusing. So I try to remember it this way. So this is done. Now, the two statements that we had over here for the NMOS, let's try to repeat these two statements for PMOS. So for saturation, now what we have? Sorry. Vs, Vg, and Vd. So saturation, VSD must be greater than equal to VSG minus modulus of Vt. Okay. Now,
Yes,
what happens is, here if you see Vs minus Vd must be greater than equal to Vs minus Vg times minus modulus of Vt. So if Vs and Vs are going to be cancelled, and if you reverse the sign, then Vd should be less than or equal to Vg plus modulus of Vt. Okay,
yes, sir.
this is what you get. Do you guys follow?
Yes, sir.
Yes, sir.
Yeah,
Sir, one question, sir.
yeah.
Sir, in the lecture series, sir said about BJT is a diffusion device, MOSFET is a drift device. Means how can we say it through in device physics panel, sir?
Device physics. So yeah, the mode of charge transportation in your BJT is occurs through diffusion. And from diffusion, what do you mean is, like, let's say there is some charge concentration at one point is higher than the charge concentration of other point. So a charge concentration difference is created, and your electrons move from the higher concentration to lower concentration. That is called a diffusion mechanism. On the other hand, in MOSFET, what happens is there is a channel. You apply an electric field, and that electric field pushes your electron from one direction to the other, depending on the direction of the electric field. Your electron actually drifts in that particular channel. So it's called a drift device. As far as circuit designers is concerned, these mechanisms don't concern us. Only we need to know is the characteristic equations of these devices, and you can design any circuit that you want. If you really want to understand the mechanism of drift and diffusion, you should take some device course.
Thank you, sir.
Yeah. So now, okay, let's get back to it. For saturation, we need your drain voltage should be less than or equal to Vg minus Vg plus modulus of Vt. In English, how will you say this? So here is a PMOS. In English, how will you say this? Your VD,
Maximum value of
yeah, your
the maximum
VD.
value of VT should
Mhm.
be uh, 1 times VT above VG.
One times more absolute value of Vt. Mind
Yeah,
it,
yes, yes.
like for PMOS, Vt is a negative quantity. When you are saying one times above Vt, you mean to say absolute value of Vt, not the actual Vt.
Okay, sir.
Okay, so
Okay, sir.
your drain voltage can go at like at max one uh, absolute Vt above whatever your gate voltage is, and your device will be in saturation. So we will write over here for saturation, assuming VSG is sorry, greater than equal to modulus of Vt, drain can go 1 modulus Vt above the gate voltage, and gate can go 1 modulus Vt below the drain potential or voltage. So this statement for a PMOS and the above statement that we mentioned for the NMOS, you should keep in mind. And if you keep in mind, solving problem will become quicker. Is this clear to you guys?
Yes, sir.
Okay.
Yes, sir.
So now we have dealt with it enough. So let's try to solve two problems, one involving NMOS and one involving PMOS, with this with this theory that we have. Okay. So there, this is which kind of MOSFET is this?
PMOS.
This is a PMOS. Okay. And I want that okay, I have some power supply VDD, and for these three cases I need to plot Ix, that is the current through this device, when I vary this DC voltage Vx from 0 to all the way up to VDD. Okay, so this exercise we are going to do. So let's start. So first case 1. What is the case 1? R1 is equal to R2. So
R2.
in this case, some value R, then again R is a PMOS. It's connected as VDD. This is Ix, Vx, and yeah. So what is the voltage at this node?
VDD minus VS by 2.
Sorry,
VDD minus Vx by 2
VDD minus Vx
by 2.
by 2. Everyone follows this? Are you sure?
No, sir, VDD minus Vx by 2.
Sir, across the gate only you're asking voltage, right?
No, no, no. The absolute voltage at this point, not across the gate.
So the potential difference across that from
You are no like I am talking this this potential with respect to ground.
okay,
Sir, then it would be VDD by 2.
Uh, okay. Then what about Vx? So you mean to say whatever change you do in Vx, your this voltage Vg won't change, is it?
no, sir, it would be Vx plus uh, VDD minus Vx by 2.
Correct. What this comes out to be? Is it clear?
Yes, sir.
Yeah. So initially, what mistake you were doing is you are just finding the incremental voltage across this. Okay. VDD minus Vx by 2. VDD minus Vx is the voltage across this series combination of resistor. And since this is a resistor divider, then voltage across this resistor will be VDD minus Vx by 2. Okay, but the absolute value of this voltage will be whatever voltage you have from ground to this point plus whatever voltage you have across this resistor. Is this clear?
Yes, sir.
Or conversely, whatever voltage you had over this point minus the voltage across this resistor, both of them will yield you same result, that is VDD plus Vx by 2. Okay, so Vg is equal to this. So what is your VSG? VSG is equal to VDD minus plus Vx by 2. That comes out to be VDD minus Vx by 2. Okay. And your drain potential, that is VSD. So the source drain potential is VDD minus Vx. Now, looking at this, can you comment whether this circuit, whatever the value of Vx may be, can this circuit ever go into triode?
Sir, it will go to into triode, sir, based on the Vx value.
Yeah. Okay. So what value of Vx it needs to have for this circuit to go into triode?
It should be VDD by 2. It should be less than VDD by 2. VDD by
Okay,
2.
let's write the equation. You are saying it will go to triode. What is the condition for it to go to triode?
Yeah, VST should be less than or equal to VSG minus VT.
Modulus of Vt.
Hmm.
Okay. So let's plug in the values. VDD minus Vx less than or equal to VDD minus Vx by 2 minus modulus of Vt. Okay. That means VDD minus Vx by 2 must be less than equal to modulus of Vt. Okay, this is what you this condition should be met for this to happen. Okay, okay. Now, when will this condition be met?
So this condition will be in cut-off region.
Yeah. So for this condition to be met, your transistor like till the time this condition will be met, your transistor will always already be in cutoff region. So there is no chance that your device can go into linear. What is the quick way to see it? What I said initially, for your device to go into linear, your drain voltage should go at least 1 modulus Vt above your gate voltage. Okay, this is the condition that needs to be satisfied, and I am saying that Vx varies all the way from 0 to VDD. So in that case, let's say so this remains the drain, this remains the gate, and in that case what will happen is this voltage will always remain higher than this voltage, because this gate voltage will be Vx plus the resistance plus the voltage drop across this resistance, which will be positive when your Vx is varying from 0 to VDD. Do you guys follow?
Yes, sir.
Okay. So your gate voltage is always going to be greater than your drain voltage. So the condition for the linear region of the triode, linear or triode region of the PMOS, that is your drain voltage should go at least 1 Vg 1 modulus Vt above Vg will never be satisfied, because your Vg will always remain greater than your Vd. Is this clear?
Yes, sir.
Everyone? Is there any doubt in
Yes,
this?
sir.
Okay. So, given this fact, now you know that this, for the range provided, this device will never go to triode region. So, in this case, how will you? This can't be met. So, device can't go to triode. Yeah. Now, let's try to plot the curve for this. I will redraw this circuit over there. So when your Vx is 0, when your Vx, and this is your Vx axis, this is your Ix axis. When your Vx is 0, what is the drain voltage? Okay, does the drain voltage matters now? You guys have made sure that your drain, your device is never going to get into triode. What does that mean? Your
That
gate.
means the drain voltage will never depend on VDD. Drain.
Come again. Sorry.
It means that drain current would never depend on drain voltage.
Drain voltage. Correct. So this voltage doesn't matter at all. This VD. Okay. Now what is VG? We calculated it as VDD plus Vx by 2. Okay. So if this is your VDD, And what is the current then? I is equal to half mu p Cox W by L times
VGS minus VT.
no, VGS minus VT is for NMOS. For PMOS,
Yes,
what did we
VSG.
VSG minus
VSG. Uh, m- Mod of VT.
mod of VT? Okay. So what is VSG?
Source to gate voltage.
VDD minus Vx by 2. Okay.
Yes.
So VDD minus Vx by 2 minus modulus of Vt whole square. Vx equal to 0 means I of 0 is equal to half mu p Cox W by L times VDD by 2 minus modulus of Vt whole squared. Okay. Is this clear?
Yes.
Yeah. So it starts somewhere from this value, that is I of 0, and from there where it goes. Now, this is the formula that you get for your this is Ix versus Vx formula. So from here where it goes, up, down, straight,
So down.
down, with what will be the curvature? Linear, quadratic, cubic?
So it would be so linear. No, quadratic, sir. It would be
Quadratic.
quadratic.
Okay. Till what time? Till what point will it go down?
So when Vx would be equal to VDD.
Sorry.
Vx would be equal to VDD.
If Vx is equal
So
to VDD, what is the value of VSG?
Yes. So half mu
No,
n
no.
C of
Vx,
WL.
Vx is equal to VDD. What is the value of VSG?
0, sir.
0. Will there be any current at that point?
No,
Why?
because it would be off, no, sir. Because
Correct.
VST,
Yeah,
So
it
there
will
will
be
be
switched
current, sir,
off.
according to the equation.
Sorry.
Sir, if we follow the equation of I, then there should be current, you know. So
Okay. Where will it cut the zero axis? What will be this value?
VDD, sir.
Are you sure?
Yes, sir. Because at that place, the only current will be 0, so that's why it would be VST. Yeah, so it should be VDD.
No. What is the condition for the current in the MOSFET to be zero?
Okay, then it should be VST should be less than equal to VT. So it should be
Correct.
VT.
It should be.
VT.
Sorry. V
Less than VT. VT.
less than.
Threshold.
No, no, but that is basically your source gate voltage. I'm talking about with respect to Vx.
sir, when the VDD minus Vx by 2 minus modulus of Vt will be equal to 0, then I will be 0.
Correct. What is this value?
So we have to calculate, I think, Vt, uh, 2 Vt plus VDD.
2 Vt plus Vdd,
Yes.
or Vdd minus 2 Vt. See, whenever you quote some answer, you
Yes, sir.
should do
VDD minus
some.
VDD.
You should okay. It's okay to calculate your answers from the equations that you have, but there is always room of some silly mistakes that you might be doing. So whenever you are quoting some answer, you should do a sanity check. For example, right now you told VDD plus some modulus plus 2 modulus of VT. But I am saying that Vx can only vary from 0 to all the way up to VDD, and we know that at VDD already the transistor has switched off and there is no current going on. So how can your answer be greater than VDD? Okay, so these kind of small sanity checks you should always keep in mind so that you can you can be immune to silly mistakes that you do in your answers. Okay,
Okay.
yeah. So the actual answer is VDD minus 2 VTH, modulus of VTH. Okay,
Yes, sir.
yeah. So this is done now. First case is complete. Your voltage goes all the way from I0. What is I0? I0 is basically half mu p C ox W by L times VDD by 2 minus VT, and it goes all the way down up to uh, VDD to 0, and it gets cuts off at VDD minus 2 VTH. Is it clear?
Yes, sir.
Correct. Okay. Perfect. Now case 2. So case 2 is let's again our case 2 is R1 is equal to 0. In this case, what will be the current? Can you guys quickly tell?
Sir, it should be 1 by 2 mu Cox W by
Uh,
L.
okay, quick question. What if R1 equal to 0, what is your VSG?
Sir, VDD.
VSG.
Yes. Sir, VDD. No, sir. It would be V VDD minus VX.
Uh, R1 is this quantity.
Yes, sir.
Yeah. So what is your VSG if this voltage goes to 0? What is your which one is your gate voltage?
It should
Sir,
be
it would
across the
be zero.
Across R1, right? If R1 is 0,
Yes,
the
yes,
voltage across R1 is 0, your VSG is equal to 0.
zero. Yes,
Correct?
yes,
So
sir.
what will be your current in case 2?
Sir, half new.
Your VSG is 0.
Sir, it should be 0, sir. Current should be 0. MOSFET
Why?
will be,
MOSFET will be turned off.
yes, sir, cutoff region.
Yes, sir.
Okay. So whatever your Vx, you can vary all the way from whatever value to whatever value you want. Your MOSFET is not going to go in this like a MOSFET will be always turned off.
Yes, sir.
Okay. In what? Okay. Now one interesting question. Now, we claimed that this is R1, this is R2, this is connected over here, and now you have Vx over here. Okay, and you said R2 is equal to 0. So your MOSFET is always going to have zero current because your VSG is 0. What if I give Vx less than 0, a negative value of Vx? What will happen then? Okay. No, wait. Not negative value of Vx. So what if I give Vx? What if my Vx is greater than VDD?
It turns on
Why?
because the source is now Vx.
Correct. So that was the point I was trying to make. It will not turn on instantaneously. It will turn off after Vx is certain value greater than VDD. It turns out to be it like you can calculate what value of Vx it has to be. But my point is that in unlike your BJT device, in where the doping, the amount of doping decides which is collector, which is emitter, and all those things, your MOSFET device is perfectly symmetrical device. And you like in practice also, when you actually design circuits, you can switch the roles of source and drain, which is actually mentioned in your circuit. Okay. Source and drain is not mentioned, not a physical thing. It only depends on which voltage is higher and which voltage is lower. For a PMOS, source is always Vs. Source is always the higher voltage, and drain is always the lower voltage. For NMOS, source is always the lower voltage, and drain is always the higher voltage. You get my point? So, let's say if Vx becomes greater than VDD, in that case, what will happen is, yeah, like although the arrow that is shown in this figure is on the top, but since now this voltage has become higher, so that means your source will become this particular thing and your drain will become this particular thing. Now, in that case, if R1 is equal to 0, then let's say this voltage Vx is equal to now the source gate voltage. Now the moment it goes 1 VDD, in that case, what will happen is uh, your source voltage will become your source gate voltage will be basically Vx plus VDD by 2 uh, minus Vx. Sorry, Vx minus your source gate voltage when Vx is greater than VDD. Then in that scenario I'm talking, source gate voltage will be Vx. Vx will be the source voltage. Vx will be the source voltage, and your gate voltage will be Vx plus VDD by 2. So your source gate voltage will be Vx minus Vx plus VDD by 2, that is equal to Vx minus VDD by 2. Now, moment this voltage becomes greater than modulus of VTH, your device will turn on. So it turns out to be, if your Vx become greater than VDD plus 2 VTH, your MOSFET will turn on again. Why? Because your gate source, your source and drain have been reversed, and now your reverse source gate voltage has become higher than your threshold voltage. Is this concept clear?
Yes, sir.
Okay. So this is how. So yeah, like till the time you are seeing that, the question was, it varies all the way from 0 to VDD. In that case, your drain was this guy over here, and your source was this guy over here. But the moment I said that now Vx can go beyond VDD, your say source or drain will interchange, and then the device again can be turned on. The current will be in the opposite direction, though. The current will flow in this direction, not in this direction. Is it clear?
Yes, sir.
Okay. So, so as far as this case is concerned, if R1 is equal to 0, your like if the Vx is varying only from 0 to VDD, your device will never turn on. I will be 0. But if your device is but if Vx is varying like going above VDD and VDD plus 2 VTH, 2 modulus of VTH for that matter, then your device will turn on again and your current will be in the opposite direction. I think with this much of logic, you can solve for R2 equal to 0. You guys can try it out like after this session for this particular case, the third case. Okay. So now we will do one more question, the last question, that is the PMOS one. Till now we did PMOS. Now we will go and do it for the NMOS case. Okay. So now again, case 1, R1 by R2 is equal to 0. What does this mean? R1 is equal to 0 and R2 is some quantity. Okay. So in that case, now again, let's say forget that Vx is going above VDD and the source and drains are not interchanged. So in this particular scenario, this is your drain voltage, this is your source voltage, this is your gate voltage. Now quickly looking at the circuit, can you tell that whether will this if Vx is only varying from 0 to VDD, will this circuit ever go into triode region?
Sorry, source and drain.
Sorry. My bad. Correct. Now, please tell simply by looking at the circuit whether your transistor will ever go to triode region.
So when R1 is equal to 0, in case 1,
Okay, if R1 is equal to 0, what will happen?
no, sir, I am asking for which case we have to consider.
Any case. Okay. For the first two cases.
Sir, for case 2, it will enter into triode region, sir.
When? Why? Okay, for NMOS, depend the two statements I gave you, right? For transistor being in saturation, what is the condition in NMOS? Your drain can go.
Yeah, drain should be less than or equal to VG minus VT, sir.
Correct, correct. So can that happen?
Sir, in case 2, it will happen, sir, I think.
When you are saying for triode, drain should be less than VG minus VT, or drain can go one threshold below your gate voltage, correct?
Yes,
In
sir.
this circuit, can that happen? Yeah, okay. If Vx is less than VDD, in which direction the currents will flow? In this particular branch, which direction current will flow? Up or down?
It will flow down, sir.
It will flow down. Okay. So, will this potential be high or this potential be high?
Yeah,
VDD will
absolutely.
be
Drain potential will be high whenever.
Drain potential is always high. Then can this equation, can this condition ever be met?
No, 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 no. Yeah, no, no.
no, sir.
Okay. Any doubt in this?
No, sir.
No, sir.
Okay. So, in this circuit again, your transistor can never go into triode region. One rule of thumb you can keep in mind that generally speaking, like whenever there is a drain source short, sorry, drain gate short, like either by complete short as in with wire of zero resistance or with some resistance. Okay, whenever there is a drain gate short, then since the conventional current that flows in a NMOS is from drain to source, that drain then gate then source. So in that case, your drain voltage will always be either equal to your gate voltage whenever there is complete short, or greater than gate voltage whenever there is a resistance. Okay. So whenever there is a there is a connection between your drain and gate, your transistors will either be in cutoff or be in saturation. They won't go into triode. A DC connection, mind you. If there is a capacitor, then it's a different story, because capacitor cannot make DC signal flow. If there is a DC connection between drain and gate, and the drain source the drain and sources are behaving the way they should, then your transistors then your transistor can never go into triode region. Is this clear?
Yes.
It's clear, right?
Yes, sir. Case one and case two are in both are in saturation, right?
Yeah, that's what I'm saying. Whenever there is a connection between drain and gate, then your transistor is always going to remain in saturation.
Yes, sir.
Okay, so again, for case one, can you guys try to find out? So, what will be your VGS? Okay, what will be the gate potential?
BDD.
Gate potential will be VDD. Source potential
VX.
Vx. Current equation
Half
half
mu n
mu n
Cox.
Cox
VDD minus VX
VDD minus Vx
minus VT
minus Vt
whole square.
whole square. W by L will also come. Okay. So again, this when Vx is equal to 0, your current will be half mu n Cox W by L times VDD minus Vt whole square, and it will keep on gradually falling till the point you hit VDD minus Vt. After that, your transistor, your VGS will become less than Vt, and then your transistor will go into cutoff.
Yes.
Okay. Uh, Again, for the next case, case 2, when R1 is equal to R2, like you can solve it, but I can just tell you your curve will look something like this. It will stop at VDD minus 2 VT and start at a value slightly lesser. So basically what is happening is, if R1 keeps on, so intuitively you can see that let's say initially R1 is 0, okay. In that case, your VSG will be having highest ever values, okay. When R1 keeps on increasing, your VSG becomes lower and lower and lower, and in those cases, since your VGS is lower, If VGS is lower, your value of current, because it only depends on VGS, will be lower and lower. So the current range you can see, this is when like R1 is equal to 0. This is when R1 is equal to R1, R2. And if R1 keeps on increasing from this, your current curve will become this. And eventually, if R1 is so high that all the voltage comes across this particular value, uh, okay, Chakraborty, I will come to your question. I will finish this first. So, if R1 is so high that all the voltage comes across this R1 only, and there is no voltage potential difference across R2, in that case, what will happen is your VGS will become 0. And if your VGS is 0, your device will never turn on. So, you will just remain at this point. Okay, is it clear?
Yes, sir. Yes, sir.
Okay. So this curve comes when R1 value keeps on reducing, keeps on increasing. If R1 is 0, your VSG is maximum, your currents are maximum. If R1 keeps on increasing, your current VSG keeps on reducing, your current keeps on reducing. So is this clear?
Yes, sir.
Okay, so these were the questions that I had. Now I will take questions from you. So Chakravarti had a question that on which parameter COX of a MOSFET depends. COX of the MOSFET depends on the thickness. So COX basically is capacitance per unit area of a MOSFET. So you guys might be familiar with the structure of a MOSFET. You have a N plus region. You have a N plus region. So I'm drawing a NMOS over here. This is a P substrate, and then you have a gate region over here. And your COX is basically the capacitance per unit area that this region below the gate sees. Okay. Now, in this case, what happens is COX is basically equal to epsilon. So, any capacitance is epsilon A by D. And if COX into A, COX into A is the capacitance, and if COX is C, COX is the per unit area. So, on what value COX depends is epsilon by D. So it basically depends on the thickness of your gate, like the oxide. So it's metal oxide semiconductor. It's a metal plate over here. Then there is an oxide. Then there is semiconductor. So it depends on the thickness of the oxide that you are putting and the permeability of this oxide. That is the epsilon. Is it clear?
Yes, sir.
Okay. Any other question? This is one more interesting point that whenever you are actually designing, whenever you are actually designing something, then for IC designer, COX parameter is fixed. I mean, you cannot touch COX parameter. Or drain area or gate area or source area. All you can do is you can play with the width and length of this the gate area that you have. With that you can so only thing that is so in this mu1 COX W by L you can only play with W and L. You have no control over mu and COX. This is controlled by the process when you are actually designing an IC. And apart from that, the voltages that you give on gate, drain, source, that is under your control. But there is no control on the mobility or the capacitance per unit area. Is this clear? Sir, due to small work, I couldn't join the session. This session will be recorded and the links will be provided to you in the course web page only. Any other question? Okay, if there is no other question, then we guys can end the session. Thank you for attending.
Sir, excuse me, sir.
Yeah, yeah, yeah.
Sir, can we ask about the pattern of exam for certificate
Pattern
exam?
of exam, like currently, I am also not sure. As we go along, I think we will discuss with the TAs and the course instructor, and we'll let you know. I think it's subjective. I'm not very sure how exam happen for this particular course. Most probably, it will be a subjective exam, and you will have to do these calculations and all those things in the exam.
Okay, sir.
Sir,
Yeah.
sir, both live sessions are happening at the same time. Is there any chance to change one live session at a different day, sir? Because we can benefit both live sessions, problem
Uh,
solving session.
I think that is fixed by the PMRF guys and the availability of the TAs. So if the other TA is not available on other day, then he might the other guy might have chosen this slot based on whatever availability he has, and that basically uh, it depends on his discretion. I can't say anything about it.
Okay, because same time is
But
happening.
yeah, like live sessions you can't attend, but like you can always go and watch the recorded lectures. Both the links will be provided to you. You can go and watch the recorded session of the other TA as well.
Yes, sir. Thank you, sir. Thank you so much.
Okay. Is there any other doubt?
No, sir.
Sir, a live session is fixed on only Mondays or any will be
Uh,
changes?
it- these are fixed on Monday, 6 to 8 p.m.
Okay, sir. Thank you.
But the recording will be there. You can watch the recording.
Okay, sir.
Okay.
Okay, guys. Then thanks for attending. So this was the tutorial one for analog electronic circuits, and we will meet on next Monday. Bye,
Sir,
guys. Yeah.
sir, for circuit analysis, I need to post on discussion forum, sir.
Sorry.
For circuit analysis for analog designers, there is this time problem solving session not yet posted, sir.
Yeah, you can post on the forum, and the respective TAs will respond.
Fine. Thank you, sir.
Okay. Okay. Thank you, guys.